yesterday I had a few people asking me to have the live stream open for the data processing as well.
Yeah.
They could listen to the question discussions. Yesterday I had a few people ask. I know.
Yeah.
It's annoying that it starts this with sound and everything. You keep hearing yourself. So, shut that up. So we've got a few more minutes to go until the hour.
Yeah, it's only 14 now, so let's wait.
Now I have my shirt on.
You didn't look in the mirror this morning, Mark.
I did.
Okay. Okay, it's at the hour. As usual, people are still trickling in, so I'll give them a few minutes. I was just reading up on the news from the United States, but there's no clear decision there yet. So the Netherlands has gone into lockdown even further with the COVID.
Just in case. Yeah.
So it's probably good to have the workshop. I've not been outside for the whole week yet, but today we'll do the walk. So
yeah.
You can take only one other person with you on the walk, Ilse.
Exactly.
Oh, that's okay. There's no other persons here at this point anyway. I could take my cats.
I don't think they count.
Not as persons, no.
Well, it was proven that they also can transmit a bit, so maybe only one cat per time.
I think for cats it's only transmission from human to cat has been.
Yeah, no, like only between them, but it couldn't affect back to human.
Unlike the minks who can do it both ways, apparently.
Yeah, we'll see how this all develops. At least the schools are still open. Cats always.
Well, and the cases were floating down.
Yeah, my cats reminded me this morning I'm their humble servant. I didn't get to do anything without providing them their food first. Okay, it's a few minutes past the hour. We've got quite a few people joining already. Good morning, everyone. Welcome to the third day of the workshop. I'll hold off on the real logistics until we've got the lectures started. It's 31 people, so then I don't need to repeat myself. But prepare yourself for the walk today. Actually, the weather here is quite nice, so I'm looking forward to being outside for a bit. I haven't been outside since Monday morning, which is quite some time, and I'm starting to notice the impact of that. So this is the question session for people who've been working during our nighttime. If there's anything that you want to discuss, issues that you've run into during the data processing, or questions about the lectures that have been had so far, this is your opportunity. So please type away in the Q&A, or we can use the data processing session C from yesterday afternoon to follow up on discussions from that particular day. I see one question popping up. Oh, now I lost it. Sorry. Somebody asking about what happens to the questions in the Q&A after they have been answered. And well, it's different for me as a panelist, because I can see the questions that are open, the questions that are answered, and the questions that have been dismissed. I'm not sure, the participants probably only see the open questions. And then when a question is answered, I'm not sure if you can still see that.
Yeah, I think it's the opposite. They only see them once we mark them like it's been answered during the streaming, or it has been answered.
Yes.
So I think only see the open one.
Yeah, so the questions and answers are not lost. We do keep track of those, but they may not be as visible to you as you need them to be. So what we'll try to do for today is to post the questions and answers also in the Mattermost. I know Kasi yesterday tried to do this carefully, but it's quite a lot of work to keep track of everything that's ongoing. So we'll do our best, but rest assured that after the workshop, we'll also collate the most important questions and answers that have been discussed and share them with you. So for reference, you can check where things ended up.
And for the first day, we also tried, Mark and I, to put all the questions and answers that were here in Zoom in the Mattermost. So you will see them as different inputs in the corresponding channel. We may have missed one because, yeah, there were a lot of sometimes. But in principle, we've already put all of them there with a summary of the answer. It was long. So you may see them there. You can even reply there.
Yeah, I must say that the Mattermost threading method is not always very clear. So you cannot always tell which answer belongs to which original post until you click on that particular post and see what's been going on before then. Okay, there is another question popping up now. Would you like to demonstrate the use of T-Clean interactively, and is it also interesting for the others? I think that's on the program this morning, actually, right?
Yes, really.
Yes.
Yeah. The first lecture.
So you're right on time there. Thanks. That's yeah. Today is all about imaging. So from self-calibration to wide field imaging and the basics, and we'll show you the T-Clean and how that works. Maybe you can give us a very short overview, Christina, of what you're planning to do.
Yeah, so I will do basically a mix between a lecture and a tutorial. So we'll give the very basics of imaging in case somebody is really new to the topic. But I assume that most of the people had to do some imaging within apes or other softwares. And so I will try, let's see if I make it work, a live cleaning using T-Clean. So how to use the viewer, how to check what's in the logger, and so the comparison with the apes should be more direct, let's say. I hope to not make it crash during the test, but let's see how it goes.
Yeah, it's a sensitive topic for crashes, especially the viewer is notorious. There was an early question. I think it was yesterday about the cycle factor that you can set in T-Clean, and Des in the tutorial mentions you should set it to an appropriately small value. But then people asked how much is that value actually when it is appropriately small. So is that something you will also address in the?
Yes, I will try, but that's that's also very not subjective, but everybody does it in a different, slightly different way. So also, yeah, to set the number of iterations, the number of minor cycles, I will try to change it like to show what actually does in the image.
Good. I see. Benito is answering questions as well. I see something popping up here in data issues. Oh, this is a follow-up from another question. I'm not quite sure if what that means. So in channel 6 under data issues, Carlos Tangalini is asking what I mean is if we have if we have significantly different fluxes in different IFs spread and a large frequency band, we provide only one model. Is that right? I assume we should take some additional care when correcting amplitudes with respect to data with a similar bandwidth. So this seems to be part of a longer discussion. Not sure if this is. Ivan Martividal is discussing this, but he's not live, is he? No, I don't see him. So we'll park that. If there is any interesting discussion going on in that topic, we'll come back to that at a later time.
So if you see in continuum EVN data, if you see wildly different amplitudes in different spectral windows for the same baseline station, then that typically is a indication that the data is badly affected by RFI. So that may point to doing some extra flagging and then doing something clever to recalibrate the amplitudes, which may actually be difficult because of the correlator normalization. It might actually work. I haven't tried it. I don't know if others have tried it, but it might actually be beneficial to then run a C-core on that band, only that subband affected by RFI again. This will be mostly for L and maybe a little bit for C-band.
By subband, do you mean spectral window or just that particular?
Oh yeah, spectral window.
Yeah, spectral.
Yeah.
Yeah, I think that. Continue.
I was going to say that people use the word channel is very confusing because that can mean a lot of things. It can mean an individual spectral channel within your spectral window, or sometimes people call a spectral window a channel, but the spectral window is also called a band or a subband or an IF, which especially the term IF is incorrect.
Your sound is dropping out, Mark.
It's going away.
He's slowly faded out.
Well.
Oh, there you are.
Okay, probably the network connection that isn't very happy. Yeah. What I was saying is that the word IF is of course not entirely correct, but that's what Ape uses.
Yes, there's quite a lot of terminology flying around, which sometimes has different words for the same thing or similar words for different things. So it's worth keeping track of using the same terminology for the same things. And I do try to do that, but if you've been using APEs and you're used to setting IFs, then moving to the spectral window definition can sometimes be terribly confusing. And for people who are doing a LOFAR data processing, they will be talking about subbands instead of spectral windows, so it gets even more confusing. So each radio telescope seems to have its own thing.
I will also comment on that one from Carlos, because I think, as I interpreted that question actually, like more related about self-calibration, like once you've done all the calibration, then you may expect at different amplitudes for different IF subband spectral windows. And then you get a model for your calibrator. You only use that model for your whole band and all timestamps that you have. So yeah, that model will predict a flux per frequency, basically, per channel. And taking into account that model, you will, in principle, correct all the different spectral windows. Self-calibration is spectral window independent. Well, yeah, independent. So you will correct them differently to fit the model. So even if you see those slight differences, fluxes, in principle, all of them will be corrected after self-calibration. Probably in the talk that you will have today, that will be discussed. And yeah, the model predicts a flux per spectral channel. So at the end, and it's subband independent. So you will correct them differently. So the slightly different normalizations that you may have at the beginning should be corrected by that. So you don't need a model per subband or spectral window.
Okay, so yeah, I think I get what the question was. There is a question in the data processing now with a plot. So data processing C, a question from Sravani. A plot of the autocorrelations on a single baseline, which show a really strong spike at 0 UV distance, and then something that looks like reasonable but lower data points at the longer UV distances.
I should have mentioned that probably in the plotting tools. That's a feature of CASA that people coming from apes are not used to. So if you think about your data set, file containing all the data, you have data that are the autocorrelations. So the amplitudes recorded per station, and then the cross correlations, which are the baseline products. So of course, the autocorrelations have higher amplitude, so normalized. And basically, that's the issue that you may be seeing there. So if you plot the UV distance, then you have 0 UV distance because those are the actual autocorrelations. So you combine the data from one station to itself. So the UV distance is 0, but then you get the amplitudes from the autocorrelations that typically are much higher than when you correlate with the baselines. So by default in apes, if you do one of those plots, it never plots the autocorrelations. You will only see the baseline-based data. In CASA by default, if you don't put additional parameters in the antenna part to exclude the autocorrelations, then you will see everything. So that's why you are seeing those data points there.
Okay, I added the answer to the question, so we can trace this back. Let me check Q&A. Sumit asking a question: how is the accuracy of AO flagger? I'm not sure what.
It hasn't been exhaustively tested in VLBI data. It's really accurate for LOFAR data, university data, where you have a really high amount of RFI, like 20, 30% of the band. So obviously in VLBI, you always have, even at L band, you have way less number of amount of RFI there. So in principle, it should work almost in the same way. Like you can always tune it to produce the best statistical constraints to flag your data. So that's something that needs to be always manually and tested in your actual data. But extrapolating the results that you see in LOFAR with a much more contaminated band, everything should work fine and be really consistent. But again, no one has tested it in detail in VLBI data.
I've had a little bit of a look, and the problem I ran into is that if you have RFI which spans the whole observation, it analyzes this by scan. And if it doesn't go over the threshold in that particular scan, you can have a very lengthy RFI signal for the whole observation, but it will not flag it because each scan itself doesn't reach the signal to noise threshold that you set for detecting the RFI. Yeah. This is something that I still want to discuss with the developer, see if this is something we can force it to look over scan boundaries and also across spectral window boundaries to see if there is a frequency or time-dependent RFI.
And the other thing is that it's more sensitive to really narrow RFI. So if you have broadband or spanning much longer time scales, then AO flagger may not detect it as accurately as really narrow spikes in your band. So I think the most tricky part is to end up with good thresholds that optimize your actual data. That's the tricky point.
Yes, and this, especially in L-band for VLBI, can be tricky if you've got some spectral windows which have lots of RFI and other spectral windows which have fewer RFI. Then the settings per spectral window actually should change, and you can only set one value, as far as I know, per observation.
I think, yeah, I think so.
So that's something we're looking into. But yesterday there was also in the Mattermost channels a post from Javier, who has worked with the RFI flagging for eMerlin, and I've added this link to the CASA automated flagging tools on the wiki page, all the way at the bottom. So you can check out also the CASA methods, internal methods for automated flagging, and see how they do for your RFI mitigation.
Yeah, I put an extra comment there because I know that a few of them, the thing is that you really need to know if those methods are working on the baseline level or they are expecting all baselines to have the same sensitivity, because that's what we knew from ACE and also from a few tasks in CASA. Like once they start doing the statistics, they are expecting all baselines to have roughly the same sensitivities. So in the case of the Merlin even, it can work. But in the case of the EVN, when you have a really sensitive dish and really poor, less sensitive ones, it may create problems. And then it can flag all the less sensitive baselines that you have just because it assumes that that's noise.
Yeah, I think I actually added the remark of Javier to the wiki that mentions this. Not quite in those words, but it does mention that certain settings you can only use after you've done your calibration, so that the sensitivity has been corrected. Yeah. It's not flagging the data that you're actually looking for. Okay, there's a follow-up on the autocorrelation plot question. The autocorrelations are showing this high spike at the 0 UV distance, and the question then is, should I flag the high amplitudes or correct them? Who wants to take that?
Sorry, can you?
Oh, so the spike of the autocorrelations at 0 amplitudes, and the question is if that should be flagged or corrected. But
the quick answer is that you don't care if it's in the autocorrelations, because at the end, all the calibration and reduction that you're doing, and when you plot, when you do the imaging, it's only taking into account the baseline data, not the autocorrelations. Yeah. So you only use the autocorrelations to basically set up the band passes or the a priori calibration. But after that, you have the data in your data set, but that one is not used unless you explicitly mention that for a task that you want to run. So for the whole procedure, you don't care about having the autocorrection data there. Actually, typically it's better to keep it there just in case you need to rerun band passes or things like that. But that, even if you see that in the plot, it doesn't affect what you are doing. And again, the only difference is that in apes, you had exactly the same thing. If you're coming from apes, for example, you had that all the times there. The only thing is that apes was hiding them automatically in the plots.
Yeah.
And CASA are showing it.
Yeah, go ahead, Mark.
Can you show where in the plot MS and how you can exclude the
Yes, I need to check that one because I know I had that and it has been a long time, but yes, I need to check the syntax.
Yeah, I think if you've got the EF ampersand star syntax, it does not plot the autocorrelations. Is that correct?
Yeah, I think that's only the baselines. But if you want, for example, all baselines, so not setting a reference antenna, that's the part that I know that there is a syntax.
Yeah, there's a trick with the ampersands. settings as well.
Say so, yeah, or like a star ampersand star, something like that. Yeah.
So yeah, that's a good point. So if we can look that up and check back on how to do that properly.
Yeah, but first I will check it because just to be sure.
Yeah.
That's
and one other thing I wanted to remark, I've been working with a data set where we use the AC core task, and then you do need your autocorrelations to be present because you use them as an extra calibration step in the data processing. And if they've been flagged, then the AC core doesn't work. So
yeah, so indeed, Des put a link in the chat now. The documentation actually has a very good explanation on how you do, well, in this case, baseline selection, but other data selection as well. And the nice thing about CASA is that the way to select specific bits of your data is pretty much uniform across all the tasks, unlike APES, which does whatever it thinks it is best for the specific task. So once you've learned it, you can use that way to select, say, only the baselines and leave out the cross correlation, autocorrelations. You can use that in all the tasks that you want.
Yep. Okay, thanks for sharing that, Des. Looking at the time, we've got 5 minutes, so there's one last question in channel 6, data issues. Let me see if I can read it without things blocking my screen. For data from VLBA, you need to run the gc2.py script on the FITS RDI files for gain curves. The T-sys measurements are built into the FITS RDI, so appending them is not required. What about translating the flagging to the CASA data format? The very first step in the tutorial. Do you need the UV flag file, or is this also in the data? So this is for VLBA data specifically.
And the answer there is that there is indeed some flagging information for most VLBA experiments in the FITS RDI file, and that will be converted automatically. I have to be careful here because I'm not sure if that's automatically applied.
So what would happen to it if you convert that? Does that mean it makes a different flag version for you, or how does that work?
No, it creates a flag table in the CASA measurement set. And then I think you still need to apply that. I will come back to this question.
Okay. Let's see, there's no stuff in the data processing.
There is one in the chat.
Oh yes, and there is one question, and that's actually a good one because that's a typical thing in the data processing for yesterday. When I tried to append T-sys values from the NTAP file to FITS RDI, I got the message crash reporter initialized, and that is a typical CASA thing. You don't need to worry about that bit. But the next bit is important. The index for antenna WB, Westerbork, does not match FITS RDI file. And later, when I generated the amplitude calibration table with YAML, I got the error. The syscal table is not present in the measurement set. So that's, the second error follows from the first, but I think Mark can explain what the index problem means and what we can potentially do about that.
Yes, so in principle, this means that, I'll put on my video, people can see me. In principle, this means that there's data in the FITS RDI file for Westerbork that does not have associated T-sys information in the NTAP file. Now, if this is a 2 gigabit per second experiment, that might actually be expected because the bandwidth of the IF, the true IF at Westerbork is actually limited to something that only allows us to do a gigabit per second. So what is it, 128 megahertz of bandwidth, which means that there's data in there for the missing bands that is flagged. And what the support scientists do is they don't provide the T-sense information for those spectral windows. And apparently we have to sort this out. I have to talk to Benito and co at our next meeting to see if we can do this better. And maybe I can turn this into a warning in the script instead of an error, and make it not leave out the thesis information completely. But the workaround for now is to change the index line of, in this case, Westerbork, such that it does provide bogus thesis information for those bands that are not around. Since the data is flagged anyway, it doesn't matter. And then the script will run and you can continue. I'll have to look at the particular experiment to see how you have to change the index line. So give me a message on the MetaMost and I'll look into it.
I'll tag you in the answer, Mark.
Yeah, to follow up, it can basically happen with Westerbork also if you have Merlin stations within the EVN. And in general, with those stations are typically travels.
Okay, I think we're running on the hour, 10. Oh, sorry, 9:30. It's here, 8:30 UT time. So we should close this question section. I'll any follow-up questions or questions that are still here floating around on my screen, I'll make sure they get into the MetaMost channels for answering by the tutors. And I'll get back to Benito for the session with the lectures.
Yep. So just stop the recording and open a new one, or we continue?
I've done that.
Ah, sorry. Okay, I was transparent. Thank you. Okay, so welcome everyone. Good morning, afternoon, night, whatever is your time zone. This is third day in the morning, and today we will basically show everything about imaging and everything that you do after imaging. So self-calibration and different types of imaging. And today we will start with Cristiana Spingola from INAF in Italy, and she will explain to you all the basics about imaging on VLBI with CASA. So Cristiana, please go ahead.
Thanks a lot, Benito. So let me try first to share the screen. Okay. Let me know if you can see it.
Yeah, perfect.
Okay, so hello everybody. I will try to address the basics of imaging of VLBI data within the software CASA. So this will be a mixed lecture and tutorial because I will try to do it live using the task clean. And okay, let me move to the next. So the goals of this lecture tutorial are to make dirty and cleaned images from VLBI dataset. Just a note, if you do not have your own calibrated measurement set, you can also download the one in the wiki. That's 3 GB, so it might take a while. Then we will visualize and analyze the images using the viewer, so the imaging CASA products of CASA. And finally, we can also export images into FITS files, and then you can use your favorite plotting routine, for example, for papers or for scientific publications. So I will just briefly mention something that was discussed already yesterday by Martí Vidal. So we have a Fourier transform relation between what an interferometer measures, so the visibilities, and the intrinsic source brightness distribution. However, as we have sparse arrays, so we have antennas, a finite number of antennas located in specific points, the UV plane is not continuously filled. This means that we cannot do a direct Fourier transform of all the visibilities to create our image. So if we want to recover the source brightness distribution, we have to to be to do another trick, let's say. So as we have this issue with the UV coverage, what we can define is a sampling function. The sampling function is what yesterday Ivan called coverage function, and this is equals to 1 where there is measurement and 0 otherwise. So what we have actually, what we see here, is that we have the covering function multiplied by our visibilities. And in the Fourier domain, this corresponds to a convolution between the source brightness distribution B with the PSF, which is the dirty beam. So which is this term here. So in principle, we know the dirty beam because we know our array, but if you followed Ivan's talk yesterday, we actually have what he called gain corruption. So we have an extra complication in here. But let's assume that we actually know the dirty beam. What we want to do in order to recover our intrinsic source brightness distribution is to deconvolve from the PSF, so the dirty beam. This happens in an iterative way, which is called the cleaning process. So here on the right, you can see an example of this process going on. There are several steps, and I think they will become more clear when I will try to do it live. But just for those who are really new to cleaning, I'll summarize the very basics of a simple cleaning algorithm, which is the Ogbom or Clark algorithm. So first, we have to initialize a residual map, which is our dirty image, so our intrinsic source brightness distribution convolved with the dirty beam, and then we can start the cleaning loop. This loop identifies the peak in this residual map. It parameterizes it as for example, a delta function, but it can be also another kind of function. It can be a Gaussian, depending on the kind of algorithm that we are using. Let's start simple. So we convolve this point source, this delta function with the beam, subtract a fraction of this, which is called the loop gain. Generally is 10%, but we can change it in T-clean, as we used to do it in Imager, and we subtract this from the residual map. Then if some stopping criteria are reached, we stop it here. Otherwise, we initialize again the cleaning loop. So at the very end, we convolve our model, which is made with these clean components, with these point sources, with these delta functions, with an estimate of the clean beam, which is usually a Gaussian fit to the main lobe of the dirty beam. We add back the residual map, and we create, we obtain a cleaned image. So this process happens into two nested loops, which are major cycles with the inner loops of minor cycles. And this happens because it's faster, so it's something that makes cleaning and deconvolution more efficient, because the minor cycles actually happen only in the image domain, while the major cycles have to go between the image domain and the Fourier space, so the visibility plane, and therefore it's computationally expensive. So if you want to know more about the deconvolution algorithm, and these are the links, and for the moment I will use a Ogbom cleaning method. So on the right you can see actually what happens with the major cycles. This is from the data tutorials, also the formula I used before. You can see that at each major cycle we can make our model, which is an increasing flux density, but each time the residuals go at lower and lower surface brightness. And therefore, in this way, we can recover the entire surface brightness of our source, even that at very low level. So what we want to do is to come from something like the image on the left, so a non-deconvolved image where we have the source brightness convolved with the dirty beam to what is called a deconvolved image, where actually we have our model, which in the case of CASA, it's a 2D image. So our model is convolved with the clean beam, and plus we add again back the residuals. So this kind of cleaning works better with compact sources. So this is an measurement set of a gravitational lens, which is an actual gravitational lens. It's not the pirate that Ivan yesterday mentioned. So it's a mix between compact and extended emission. And I chose this measurement set to show you how a delta parametrization actually works. So the task that we will use is T-clean. And it corresponds to imager within APES. And there are several parameters to be set. We have the visibilities part here in the top. So the yellow part where we have to select our data. So we have to select the field if you are using a multi-source measurement set. So if you have, for example, the calibrators and the target. You can also select the spectral windows with SPWs, time range, UV range, antennas to be included, excluded. Here you can select the data as you prefer. Then we have to decide what data column to be used. I think something about this was already mentioned in Mattermost, that if you have, if you're using the measurement set when you run apply-cal, so the multi-source measurement set, then you have to choose the corrected data column because that's the one that includes calibration. But if you have split the target only, then what is left in the new measurement set with the target only is only the data column, which is the previously corrected data column. So in case you have the split measurement set, here you set data. This is what I will do later, actually. So we have the image parameters, image, of course, the image name, image parameters, so image size, cell size, and phase center. You can here put phase center in 2000 coordinates, for example. Here on the slides, just a recap on how to set pixel scale, so the cell size and the field of view, so the image size, which depend both of the parameters on your data specifically. In the case of the cell size, you can take a look at in plot MS at the maximum UV wavelength, and so set the usually the cell size is set according to the highest angular resolution that you can achieve. Of course, you have a range of scales that your data samples, so your interferometer samples. So that's also a critical parameter here. Another thing that you have to select is the Nyquist sampling factor. So here this makes sure that your PSF is sampled by at least 3 elements, so 3 pixels, or maximum, let's say, 5 pixels. But if you sample more your main lobe of the beam, so your clean beam, then you can encounter other difficulties in the imaging, which is called oversampling. So you may have in your image some artifacts that you didn't want to have, so that's not real. So just keep in mind that this is actually tricky, even if it seems simple to set. Then we have the field of view, which is the image size. We will have later a wide field imaging lecture, so you will learn a lot about this also later. But this parameter here depends on your bandwidth and time smearing limits, also your primary beam limits, and of course the expected size of your source. So I will just go on with a multi-frequency synthesis kind of analysis, so MFS. As Ivan said yesterday, this is the way to take into account the spectral dependency of our source, also because we have now very large bandwidth, so that's critical. So as I will talk about a standard radio continuum imaging, I will not go through what is related to the spectral line imaging, but here you have, for example, RefRec that you can set in case you have spectral line imaging and you are creating a cube, that you can do it with spec mode. So the grider, I will use standard grider, but again, I think some more complicated grider options will be discussed later. I will not apply any primary beam correction. And the deconvolver here, you can select the algorithm that cleaning will use. So I will use an OCBOM one, but here you can have many, and one particularly, especially important in the case you have extended and compact sources, is the multi-scale cleaning, which is implemented here. You can also restore, decide the size of your clean beam with restoration, and then now I will discuss just before the weighting the number of iterations. So this is a bit tricky to set. Of course, if you put it equal to 0, you will produce a dirty image because you are not deconvolving from the PSF. If you select it larger than 0, all set of parameters will be unlocked, especially those that are related to the minor cycles, and so the threshold and so on. So here I usually, as a rule of thumb, do not use a number that is larger than the number of visibilities in my data set, but basically you don't want to be limited by the number of iterations of the cleaning. You want to stop according to a certain criterion, for example, the threshold, which can be based on the RMS of your data set, or if we do it, you do it interactively, as I will try to do. You can stop when you see that within your mask, the source, you have cleaned all the flux density of your source, and basically what is left is only noise. So you want to use different kind of stopping criteria. That's why number of iterations here should be a large number. So you can select the weighting scheme. So here you can use natural, uniform, and Briggs weighting. So the Briggs weighting is a little bit different from what is implemented in imagery in apes. So let me know, I don't know if anybody else has something more updated about the robust, but as far as I know, in CASA, robust is the Briggs parameter is between -2 and +2, where 0.5 in CASA corresponds to robust 0 within apes. So the -2 is the totally uniform, the +2 is totally natural weighting scheme, and then finally, we have the last two parameters, restart, which if it's equals to true, then the cleaning process will start from your last image. So you should keep in mind that you should change the names of the images. So in image name here, right below data column, otherwise you will start back from the cleaning from the previous image. So this is up to you depending on what you want to do. I usually keep track of cleaning, changing the names, and having different cleaned images. And the last but not least, safe model is crucial when you do self-calibration. So I believe that Javier will tell about this later. So if you do not select anything, so safe model equals to known, your model will not be attached to your measurement set. But if you select safe models equal to model column, then it will create a new column within your measurement set, which is called the model column. And so that will be then used to do self-calibration. So here now I will try, so I will stop share for a second, and I will try to do an interactive cleaning. Let me see if, okay, I have to share this. And then can you let me know if you see the terminal.
Yeah, we see a terminal and stuff on your screen.
Okay. So what I have done already before, it's like, you know, when you do these demonstrations of cooking, is to run clean with number of iteration equals to 0, so that we create a dirty image. And with viewer, which I think Benito showed the use of viewer also to inspect measurement sets, you can actually open the images. And here we have dirty image, dirty.image, sorry, and then we have a number of surfaces attached to our dirty name, and we will inspect all of them. So we can load them by using raster image, so dirty.model, raster, and then primary beam. Then we add the PSF.PSF, which is self-explicative, the residual, and the sum WT is a single pixel. You can see it here from shape. It's a single pixel image that contains the sum of all the weights of the visibilities. So we will not use it open here. So here we have our viewer, which is our graphic interface for cleaning, and therefore also for the later self-calibration steps. We have a lot of buttons, so I will show you what I usually use to inspect the images. And so first the zoom buttons here with the lens on the right, but also this one here, the second row, the first one, where we can draw a rectangle, double click and zoom on our system. Here we have this lensing system that is a jetted AGN that is quadruply imaged. And so here we can zoom, for example, on the brightest emission. You can see that is a little bit extended. And here we have our beam in the bottom left corner. We can zoom out. We can move with the hand here across the image, and then we can, for example, as you may have noticed, our source is not exactly at the face center, so we can either click on view cursors, and it will show the cursors in all images. So as this is a little bit too much, we can also use this point marker here, and if you pass with the cursor over the buttons, it will show what the buttons actually do in case you forget, or if you don't remember, or you don't know. And then you can put for example, point marker here. You will get information about this region, which is actually a single point, but we have the center XY, so in our JW coordinates, but we have also the statistics about this region. So to remove a region, you pass with the cursor over and then type S in your keyboard, and it will be removed. So let me zoom in and, for example, draw a rectangular region in image D, that is the less bright image. Here we can get the statistics about what is within this region. So it's basically what TV stat in Imager does, or ImStat in case you are doing it on the entire image. So we have a lot of information here. The observing frequency, the brightness unit is in Jansky per beam, the beam area in terms of number of pixels, the number of pixels within this rectangular region, the sum of the values of the pixels here, the integrated flux density in Jansky, the mean flux density, the RMS and standard deviation, minimum and maximum values of the pixels, so this is in Jansky per beam, and how many regions we are actually selecting, which is 1. So now with animators, in case you do not have these animators by default, you can go in the top panel with view and then display animators. Let me remove it, and the tick on the left should be on. We can move through the several images that have been produced during the cleaning. But we didn't do any cleaning. We did just run, I just ran the T-clean with a number of iterations equal to 0. So the model does not exist, of course. We did not have applied the primary beam correction, so the .pb image is empty as well. The PSF, sorry, let me zoom out, is our dirty beam here. And so you can check this in different ways. And then we have the residuals, and the residuals in this case, of course, are equal to our dirty image. So I think this was the last, yes, the last image. So I will close the viewer, and I will just run I will do tget tclean to restore the parameters that I have previously inserted. Imp tclean. So here, okay, I didn't save anything. Yes. So I will just do the input. So I will set the visibilities, the image name. I will call it clean2.nat. So the other surfaces will be attached automatically during the cleaning process. So I will just give the first part of the name, then a name size and the cell size, the number of iteration. I will set it to 100,000 iterations, and here you can see that we have now several informations, several new parameters that are related to the minor cycles stopping criteria, for example. So here we have the gain loop. I will leave it to 10%. This threshold here, I will not set it, but here you can set either manually a threshold or a threshold that is based on number of sigmas. The maximum number of minor iterations, I will leave it to -1, because it's something that we can also select manually while doing cleaning. I will show it in a moment. And then here there are all these values that are now set to the default values, and basically what they do is to allow CASA to select a way to stop the minor cycles. So these are based on the peak of the residual image and the fraction of the PSF that is used to convolve it with the PSF. And basically, if we do not set anything, the software will automatically estimate a threshold where to stop the number of the minor cycles and start a major cycle. So I find it, I never changed those values by hand. You can play around, but I think that the way the tclean uses them is already fine. But we can then change the number of minor cycles within the major cycles by hand. I will show you in a moment. So let me just check that I selected also interactive equals to true. So otherwise it will do a cleaning without opening the viewer, and so we will not be able to stop it unless we do a Control-C, I think. And actually, if you, in that case, if you have selected the save model equals to model column, then you will very likely corrupt your measurement set. So I do not recommend doing that. And then let's see, we just type go tclean, and it will give us in the logger the recap of what we have inserted, so all the parameters, an error message that we do not need to worry about. Number of rows selected is the actual number of visibilities, and of course the first here on the left you can see the progress in percentage. I actually find this very, very useful. You can go grab a cup of coffee in the meantime, because of course the most consuming step is to create to make the PSF, to make the dirty image. And you can see here that it's now doing it in the logger. So you can see that it's doing this step here. And what it's, we have set, the weights to natural weights. Of course, you may want to change it to different kind of weights if you are more interested in the highest angular resolution image that you can obtain. You want to select the uniform weighting scheme, or you can play around with UV taper, which is very handy the way it's implemented here in terms of meters and arc seconds. Okay, so the dirty beam has been created. Here you can see the properties and also the theoretical sensitivity has been estimated by CASA, and it starts, the first major cycle. So in a moment when this will be finished, a new viewer will open again. So we use viewer for both doing the cleaning and inspecting the images. So it's a very powerful tool. And in the new viewer, we will have the new viewer window, we will have a new box, green box in the top right corner. And in that part, we will be able to set the parameters for the minor cycles and to stop and continue cleaning. So let's see if it will open. Yes, this seems a good sign. Okay, so this is the first residual map that I will talk about before using the slides, which is the initialized residual map. Here is the dirty image, so that's what we just saw before. This is the green box here. So here you can see that we have, this is the maximum of iteration, of total iterations left, 100,000. The maximum number of iterations within the minor cycle is set automatically to 100. The threshold here is 0 because we didn't set it, but actually Ticklin sets for the first round a automatic cycle threshold. I find this that is always okay. We have in this part, I don't know if you can read it because it's very small. We have here the first box, add and erase, which is related to the clean boxes, so the mask that we will create. And we can add these boxes either to a single channel in case of a cube, or we can create different boxes for multiple channels. This is very useful when doing emission lines and cleaning of spectral line, and this is set by here. It's the same with the polarization. So what I will do now is to zoom where I believe to the emissions to be true, and sorry, just a clarification. I will do, let's say, old-fashioned cleaning but interactively by setting boxes, so a mask, and this will help the algorithm to converge faster. But of course, you can also decide to not use the boxes and do it non-interactively by setting a threshold. Of course, the threshold is very important, otherwise you will likely over-clean or under-clean your image. But this is just to show you how to do it interactively. Otherwise, the non-interactive part will not be very much of fun. So here I select a box in, let's say, in an apes fashion way. I select an oval box here. Of course, it's green over green. Double click, and you can see here that the white contour has been created. And this sets the first box, the first part of the mask. So I can use also rectangles, but I think that there is one very nice feature of cleaning in CASA, that is this polygon rectangle here. So the regions are those buttons with the R within, and the polygon drawing is really useful when you have very weird shapes for your sources, for example, gravitational arcs. You don't want to have thousands of boxes across your source, but in this case, you can create a single region that has the shape that you want to select. So let's go through the 4 images. So I will start to create the polygon region. I'm doing it roughly just because we do not have too much time. So with double click, you close the polygon, and with double click again, you create the mask. And you can see it here that in white, maybe it's done. So we can anyways doing it also with ellipses. And then so this part here, everybody does it in a different way. I guess that if we all clean the data sets, we would also set the boxes in a different way. So I'll just show you how I would do it. And so I will first add the boxes where I believe the emission to be true. In this image, which is this component of our lensing system, which is image C, you can actually maybe notice that we have this tiny tail. I'm not sure if this is a true emission, so I will not include it in my mask. This is at low surface brightness, so if real, it will appear in the residuals at later stages. But something that is very important, especially in the self-calibration process, is to make a good model of our source. So it's very difficult then to get rid of a false component if you add something that is not real from the beginning. So here, what now? If we are happy with the mask, then we continue with cleaning. So we actually set, as the emission is quite bright, we can set the maximum number of minor cycle iterations to a larger value. So I usually stay here between 200 and 10. So this is the range that I typically use. I'm open to suggestions here, and I guess that everybody has different opinions on this, but I wouldn't go further because otherwise you do not have any control anymore on the cleaning, even though I believe that CASA will kick you out for minor cycles iterations when it finds that your peak residual is equal to the peak of the side lobes, because of course it knows where the side lobes, the amplitude of the side lobes. But anyways, I wouldn't go further than this. So what we did is to press the green button here on the top right, and this will continue the deconvolution with the mask that we have just put on the image, and it will open a viewer again. But if you actually click on the blue arrow, then it will go on with a non-interactive cleaning, and then you will not see the viewer again, and that's not good. So we go back to the logger, and you see that we have run the major cycle number 1. We started with a total model flux density that is 0, but now our model from 0 went to 28 millijanskis. Here you can see the peak of the residuals, which started from 16 and now is going to 4 millijanski per beam. And so one thing that you may encounter is that the cleaning does not always converge. Sometimes it doesn't, and one of the ways to check when things go wrong is to check if the peak of the residuals is going higher than the previous step. It shouldn't be. Same story with the model. The flux density should be always increasing and never decreasing. So now he has finished, and you you can see here that it did 39 iterations. So it computes the way automatically, the way to kick you out. But in case it could go further, we could let's say if the peak of the residuals wasn't at the same level of some side lobes, we could go further with our minor cycles. So we are now at the next step, where we have removed a fraction of our components, of our models, and we have stored it in the dot model image. So what AIDS used to do is to create a clean component list. Here we have actually an image of our model. That is very nice to inspect. So we are going at lower surface brightness, so we can include the new emission at lower surface brightness in our boxes. And let me try something here. So now I'll go to image A, but by mistake I add a region like this, or including way too much emission. Of course, this is not what we want to do. So we can erase the regions by clicking here on erase, and so we can erase our region, and then with polygon R here, and with add again, otherwise we will double click, but nothing will happen because it erases the regions. We add back again the mask here. So this is the interactive cleaning. So we can every single at the end of every major cycle, we can check what is the stage, how is the emission within the mask that we have selected. You can see that here we have now a little bit of extended emission. Maybe I can zoom in. So here, and of course you can be much more precise than what I am doing at the moment. This is just like a demonstration for how to do the interactive cleaning with CASA. And of course, let me click on continue. So in the meantime, it goes on. Of course, you clearly see here that we didn't reach the noise level within our mask. So there is still emission to be cleaned, and so we need to go to continue cleaning. You can also change the stretch of your map. I think that the stretch that is automatically set by CASA as also in imagery names is already fine and does not bias towards very low surface brightness emission. That might not be true, but you can change the stretch by using this button here for the settings, and I will show you in a bit. So it has finished to run the major cycle number 2. So again, these cycles take a while because they jump from the Fourier space and the image domain, and our model flux density here you can check that has increased. You see here that the cycle number of iterations was 200. This time we did it 188 iterations. The peak residuals goes lower, which is good, and then we can wait for the green area to appear. If we want to know at what stage we are, we can check the terminal, and it will tell us in percentage where we are. I think not that far. And let's see. Okay, so here the viewer displays again. One other thing I wanted to, you will likely notice when you will do it, is that if you run cleaning in a window, in a desktop window, and then you are doing something else because it will take ages to run because it's a super large data set, when the new viewer window is ready, it will actually show up and tell you to go on. So you will know automatically that it has finished. So now you can see here, and that is why I like this system, because there are several subcomponents in the lens images that are at lower surface brightness, and here we go with one in image B. So this is the second brightest lens image. So in this case, by doing it interactively, of course, we can add this new emission in our mask. But what if we run the blue arrow here without including this component? We would have lost a little bit of information, and our cleaning would not have gone very well. So we include this component here in our mask, and now we have this new mask for this component. Maybe there is this one here as well. I know that this is not perfect. Sorry, I'm not very fast at seeing all the emission. Usually it takes much more time to do it properly, so take your time to do the cleaning, and it can be one of the most it is one of the most time-consuming parts, but I think it's also a lot of fun. So here, for example, let's say that we believe this emission, we add all this emission, so you can see that we have extended emission in these images as well. And so in this case, for example, let's go for a polygon region, and so we can enlarge the region, and with ESC of your keyboard you can exit from the polygon region. So I wanted to show you that you can change the stretch here with this display settings. You will see that we have clean nut dot residual, because of course here we are doing the cleaning. So each time we are actually looking at a residual image where the model has been subtracted from our data, and so we are going to clean the residual image. And we also have our mask that is composed by the white part, the white contours here, the cleaned boxes. Here we scale in power cycles. For example, we can change the stretch to different values. Maybe you don't like these colors, or you're colorblind, or you really prefer to work in another color scale. You can change the color scale. So you can use, for example, grayscale. Maybe you visualize this better. The default is rainbow 2. And then I will discuss also later other options here. But if we'll have time, I see that I don't have so much time left. So I will just click again the arrow. We can check here that we start the major cycle again. We have 72 millijansky, and so now at this time he completed 388 iterations. So it's somehow estimating the numbers of cycles that he has to do in an automatic way by using those parameters with the peak fraction of the PSF and the peak of the residual images, so that we do not have to worry about this. But of course, this is something advanced that you can also change it at a later stage. So once this one is finished, I will just show you the cleaned image and how to inspect the cleaned image. So I will interrupt this cleaning even if we didn't reach the level of when we have cleaned the entire flux density within the regions, and just because we do not have time. But of course, you can see from this image is clear that we have a lot of flux density that we have still to clean, or at least we are at lower surface brightness, so maybe it's not that much, but it's clearly there. So it starts the new cycle. Maybe we will see the new residual image in a moment. Yes, and you can see here that as far as we go at lower surface brightness. We have again again image with the arrows of your keyboard. You can move around. Maybe there is a little bit of emission as well there here in the inner part. But I will just stop cleaning, and with this action here, what it will do is to convolve the clean components, which actually is our model, with the clean beam. So this estimate of the main lobe of the dirty beam, and add back the residual image. So here you can see this is the measurement, the estimate of our clean beam with its position angle. This is the total model flux density that is in our image. Let me open the image that I have created while going down to the noise. This time we will have a dot model image that is actually filled, so it's not empty. And of course you can see immediately here, I didn't open a dirty image, but you can see immediately here that the noise is much lower. Actually, let me open the dirty image as well, so we can do a direct comparison between all the images. So we can go to the display options here, data display options. In the top part, you see that we have all the image name of the images that have been rastered. So you can also load the images as contours. You can change the stretch, for example, to -2. And if you select the global color settings, all the images will be put on the same scale. So I think this is
1 minute.
Yeah.
1 minute.
Okay. So here, just let me show you the model image. That is sum of several delta functions, so delta components. And with the regions here, you can see with statistics the properties of the images. For example, here the RMS is of about 36 microjanskys per beam. If we go through the dirty image, it was 0.1 millijanskys per beam. With this one here, you can also save the image in PNG, and you can use all the regions to estimate here. With the statistics you can check. Very last thing, if you want to export your images in fits file. The task is export fits, and there is here you can see that you can give the name of your fits images. You have several parameters that you can change, and this will change the keywords in your fits header. One particularly important is drop the generate axis and drop stocks, which by definition, by default, for VLBI images is set to 4 instead of 2, which is what typically plotting routine uses. And yeah, then I will stop here.
Thank you very much. It was a very clear lecture. So I think everyone understood everything that you need to do and be careful during cleaning. So I've seen a number of questions, both in the Q&A and Mattermost. So it's probably you can read some of them.
Yeah, the first one that came in from Arnaud Couriot. Is there a way to automatically set the clean boxes, for example, around residual peaks?
I've never tried it myself. So in general, I go either with boxes setting by hand, let's say in the interactive way as we did, or no boxes at all. So I don't know if there is a way to set the clean boxes. But if you do not use, if you do not use clean boxes, but you use a threshold, for example, then it's kind of you are setting a limit each single time for deciding where is the minimum peak flux then peak surface brightness that you want to set. So it's I think it's effective even without adding the boxes. But yeah, I don't know if any of you knows this.
So as far as I know, within CASA or within T-Clean, there's you can either set automatic boxes based upon the signal to noise. So there's an N sigma parameter which will allow you to set this. No, auto multi-thresh, sorry, that's the wrong one. So it's called auto multi-thresh and the use mass parameter. And then you can set that to be some sigma of your source, but again, that's dependent on how well behaved your PSF is. So for VLBI arrays, sometimes it does mess up because it's CASA T-Clean was built for VLA, which has lovely, beautiful Gaussian PSFs. Meanwhile, VLBI doesn't. So there is some ways of doing it, but also there's also other ways in WS Clean and things like this to set them automatically.
Does this create a box, or does this just give a threshold for like a sigma threshold?
No, it gives a box, yeah.
Okay.
And then you can use the auto thresholding then to say when to stop cleaning too on top. But it's a bit fiddly, that's the best way to describe it.
Okay, I think that's clear. There is a few questions about the masking. So Michael Lisakov is asking, how does T-Clean perform in unsupervised mode with no boxes provided?
Okay, that's a good one. When you set a threshold, of course, so I just stress this just to not leave like people doing cleaning with number of iterations to a very large number without any threshold. Then I find it that for example with a 3 sigma threshold or a 2 sigma threshold, it behaves very well. Like I get an image that is very close to what I obtain with clean boxes. The point of putting the boxes is to make the convergence of the cleaning faster. So it's okay to use it in an unsupervised mode, but it's much lower because it scans the entire image to check for the brightest pixel, the brightest peak, because it's a delta function, the algorithm that I used. So basically it checks it searches for a pixel. And so if you have very large image, then it can take a while, but it's okay.
Okay. And related to that, in the Mattermost, Victor Perez is asking, can you save the coordinates of your masks in order to use them later in non-interactive mode?
Sorry, can you say the first part again? I missed it.
Can you save the coordinates of the masks, the polygons or the boxes?
Yes, Yes, indeed. Actually, the dot mask image, like the first, let's say that you clean the first time, so that you have created from the first cleaning your mask that you want to use for self-calibration, then the dot mask will be registered in the same size and pixel scale of the image that you have created. So the issue here, and I don't know if any of the other panelists or people know here, is that if you are creating then an image that has different pixel scale and different image size, then you cannot use the same mask that you have created. But otherwise, you have a hard copy of your dot mask saved in the folder, in the directory where you are working.
Yeah. Yeah, so the trick here is that it's not the actual coordinates, but it's the image coordinates, the pixel size and number of pixels where it's located. Okay.
I think, can I just add on to that as well? It's also, if you wanted to make, say if you had a previous image of your target field, you can also make your own mask by doing it in the viewer, and then using the CASA task make mask, you can then convert that into a clean mask. If you wanted to do something before you'd even clean the field, but you kind of know what it already should look like.
So that's task. It's called make mask.
Yeah.
Okay, I've added that to the answers. The next one up is a question from also from Michael Lisakov. Is it possible to switch the units in CASA from arcsecond to microarcseconds and Janskis from millijanskis?
I actually do not know. I think the default is that, but I do not know if it can handle different units. Like if you load an image where you change the header, basically, and you change the, of course, values of the pixels from Janskis to millijanskis, and you did the proper conversion. I don't know. That can you do it?
I don't know. Never tried.
I never tried it. Yeah, what I tried is to change everything in like for example the units in using PyFits, then loading the image back again in CASA Viewer, and it shows the right values, but it doesn't show the units millijansky. Maybe Benito was saying something.
No, I'm also not sure. I've never tried it.
Okay. Let me see then. Here in the Mattermost, there's a question from Dalei Li. To get more extended emission, what are the differences between using the T-clean parameters UV taper and restoring beam? For example, image with beam size, or maybe it's easy if you read along here, with lot of 1.7 by 1.2 square microarc second. This is hard to read. Apologies. Let me first read. Not quite sure.
Let me see. Well,
the first part of the question is actually the actual question, and then it follows with an example. Okay. So to get more extended emission, what are the differences between using the T-clean parameters UV taper and restoring beam? So this is about the tapering and what the impact is on your final image.
Yeah, so they work in two different ways, and they do different things. So the UV taper actually is a let's say selection of the UV wavelength that you prefer to use, you want to use. So it's not a UV cut. It will it doesn't eliminate, for example, the longest baselines. For example, let's assume that we are tapering towards the shortest baselines because we have an extended emission. So you will weight more the shorter baselines more than in the way that you would do with natural weights, because you are selecting the scales that you want to reach with your tapering. Of course, this will change the size of your restoring final clean beam, because that depends on the base, how you weight the baselines. So that is, I think, the best way to search and to address the extended emission in sources, while the restoring beam is something very useful, for example, in the case you have to create a spectral index map where you have to obtain 2 images at 2 different frequencies with the same beam. So what it will do is to, I'm not very much experienced in doing this in CASA, but in theory, it should restore the main, the clean beam. It should create the clean beam with the parameters that you set with the restoring beam. And then I'm not sure that it can handle the noise of the images in the same way the UV taper does. But the idea is that you are forcing a beam, a certain size of the beam, for example, a circular beam, for using that image for other purposes. But for the extended emission, I would work with multi-scale cleaning and you play a little bit around with the UV tapering rather than using the restoring beam. But I'm not sure if this answers.
Yeah, I think, well, we can get back to the discussion on Mattermost if this doesn't quite answer the question. There was actually a question also about multi-scale clean, and this has been answered on the Mattermost. So somebody asked about if there is a way to do extended emission with Gaussian components, and there is indeed. This is multi-scale clean, and this has been around for a decade or so, and I think it is also possible in T-clean, right? Yeah.
Yes.
Okay. Oh wow, there's lots of questions coming in. We've not much time, so I'll just continue down in chronological order. On the Q&A, Stefano Giaratana is asking, which kind of artifacts do we get by oversampling, taking more than 5 pixels per beam, for example?
Okay, so you can imagine that basically what we are doing with oversampling is to sample the very same part of the source with multiple pixels, so we are not extracting new information. So something that I happen to have, maybe other people had different experiences, is that you really create a new component in your around your images. This is especially complicated when you work at a low signal to noise ratio, and so that's the kind of effect that I encountered, but not sure if there are other experiences on that.
I've got one thing on top, is that especially with the VLBI PSFs being extremely non-Gaussian, often oversampling allows you to fit to the peak of the PSF to kind of get the representative resolution much better than you would do if you had some nice Gaussian PSF, because at least through Nyquist sampling, you need to have 3 pixels going across to fit to a Gaussian, but when you have horrible side lobes and things, you definitely sometimes need to have more to be able to do this.
Yeah, that's a good point. Thanks, Jack.
Can you follow up on that? I'll type my answer in the Q&A. Can you follow up with that, Jack? Because I didn't quite get.
Sure, no problem. Yeah, I'll put it in.
Thanks. Let me see that I'm doing this in the right order. Okay, there's also a comment now on the autoboxing in CASA in the Mattermost chats. A question from an anonymous person. Is there an interactive way to see if the accumulated clean flux with the number of iterations as the cleaning is running? So can you see the accumulated clean flux while it is running?
Well, you can see this in the logger. I'm not sure if you want to see each single component that has been added to the model. I don't think that you can see that. I think that you can see at the end of each major cycle what is the total flux that has been increased, like as I showed you before. So maybe you can check again the logger in a separate time with posing. So you can check the total flux density that has been accumulated during the major cycle. That you can check. And you should check that it's always increasing. Yeah.
Okay. I think that should be clear. Do we have time for one last question, Benito?
Oh, 1 minute, so maybe last one.
Quick one. Sijia Peng is asking about your source, which you showed as an example. Is that an AGN galaxy through a gravitational lens?
Yeah, it's an AGN jet. Actually, there are beautifully global VLBI images from NDBX of this AGN with multiple knots, and yes, it's lensed by a foreground object that is a galaxy. The redshift unfortunately is not very well known. The background source is at redshift 3 something, and yeah.
Okay.
Thank you. So with that, we end the question section. So we may move to the next lecture done by Javier Moldón. And he's going to talk about self-calibration. So everything that you do after you obtain the first image in your data and how you improve the calibration. And Javi, if you are there, you can start sharing.
Okay.
Yeah, the lecture, I will give you a 5-minute warning.
Okay, thanks. So I think you can see my full screen now. So yeah, this is just a continuation of what Christiana was showing. So when you have a first image, then you can improve that image by doing a series of self-calibrations. And this is what we are going to show here. So for this talk, you are supposed to already know how interferometry works and the basic principles and what are the visibilities, how to decompose them, and also how to use the CASA environment, the tools and the syntax. So everything that we have been doing these last 2 days, we are supposed to know that. And also how to perform general calibration, as was explained yesterday, and how to perform imaging, that was explained right now. But of course, I will comment on all these points, so don't worry if you have still don't have much experience on all these steps. And what you will learn is why a data model is needed to calibrate a source. In most of the cases, the target sources need a model, a good model to do this. What are the steps to do a self-calibration loop? And then how to implement it and some practicality. So how to decide how to choose some of the parameters. And of course, how to implement all this in CASA tasks. So the motivation is that the quality of the image, when you are doing phase referencing, so you are using an external calibrator to calibrate your target, the quality of the image is not the ideal one because there are residual errors. Because you are transferring solutions that are not exactly correct in the same thing in your target and in your calibrator, you will have residuals. And those residuals cannot be corrected by using external calibrators, but only with actual data that is observed together with your target. Fortunately, if this only happens if your source is bright enough and you have enough signal to noise, then you will be able to calibrate the visibilities themselves to obtain a better image. And this is a little bit like a black magic, because what you are actually doing is you have data and you produce an image with those data, and you use that image to correct the data again. So this is like a bit like general relativity. You know? The masses tell the space-time how to curve, and the space-time tells the matter how to move. So this is seems to be a reciprocal thing. But this actually works, because what we are solving is gains from individual antennas. So we are correcting the complex gain, so amplitude and phases for each antenna. And that means that for amplitudes, we have, if we have n antennas, we have n parameters to solve. For phases, we have n-1 because we have the closer phases. But in general, what it means is that we are going to find these gains using a larger number of visibilities. So in the end, what you're observing is n times n-1/2 visibilities for each sample, so each spectral window and each timestamp. And because this number is higher than the number of solutions that you need, then you can oversample the solutions, and that's why it works. And also very important is that you don't need to have a perfect image of the source or model of the source. Even an approximate source will improve the calibration. So in the end, this is an iterative process. You will start with an image that is not perfect, use that image to improve the image, and then with the next one, you will continue the loop. But of course, as Ivan was mentioned yesterday, either errors in the model, so if your model is not actually accounting for the real structure of the source, or if you have low signal to noise, self-calibration is dangerous, because what you are doing is, as I said, modifying the data according to what you think the model is. If that's not correct, or you have noise that disguise the signal, then you will propagate the solutions, and you can diverge from the correct model. So be very careful, because self-calibration may be dangerous if not done right, or if you don't take the right considerations. So first of all, I will do a very quick data structure in CASA, mostly because the plots are nice. I think it's always important to visualize the data and understand how your data looks like. So of course, you know, I will skip this quite quickly, because You should already know all this. Visibilities are complex numbers with amplitude and phase, and these visibilities can change with time and frequency. And that's what we have been calibrating in the past. For example, here you have a plot of amplitude against frequency, and then you can see clearly the bandpass shape. So the bandpass is instrumental, so in principle you shouldn't expect variation with time. So that means that because you have already calibrated this in the original calibration, we are not going to calibrate further the bandpasses during self-calibration. I've never seen a case in which you need, maybe in some rare cases you may need to do that, but in principle, if you have a good bandpass calibrator, you don't need to calibrate the bandpasses. This is how phases changes with frequency, and of course this slope is the delay. And delay has, Benito was showing it yesterday, several components, instrumental, atmospheric, source structure, and so on. But in general, the changes are longer than your scan time. So with the phase referencing technique, because you have calibrated the delays along the observation, you will not need to calibrate them further. But in some cases, maybe it can happen that you may need. So yes, you will need to calibrate this further, but it's also very strange. It's not common to need to do that. So what we are going to calibrate with phase references are the amplitudes and phases with time. So here you can see a baseline, the data from one baseline, and the amplitudes change in long time scales, but they also have some variability. Maybe you cannot see it very well, but there is some intra-scan variability. So that's something that we need to correct with self-cal, and also phases. This is phase against time, and you see that the variability is huge. It changes very quickly, both in long time scales, so you have all this structure, but also in short. So for example, here you can see it going up and down within one scan. Okay, a few more plots. This is the same data, dynamic spectrum frequency against, in this case is raw number, but you can consider this is time. If you cut a slice, vertical slice, this is basically the bandpass. And if you cut a slice, horizontal slice, you will see the time variation of the amplitudes. And here you can see the projection. So this is the dynamic spectrum of amplitudes, bandpass, and change with time. And also with phases, this is the dynamic phase plot. So frequency, time, and then you have the phases. And again, the vertical slices will be the delay, and the horizontal slices will be the time variation of phases. So you can see here the projections. Okay, this is just because I think it's important that you always look at your data to understand what is happening and if all this has been corrected or not. So as I said, the bandpass and the delay should already have been corrected. The phases should be almost zero, but you see that there are still residuals. You will see it later. So another way to explore the data is you saw this yesterday with CASA-VLBI. You can call it from CASA or from the terminal. You can select here the columns, and in self-calibration, it's very important that you understand these columns. With CASA browser, you can open a measurement set and see these columns actually. So the data, this is your raw data. Corrected data is the data that has been corrected with the normal calibration. And model data is where, as Christiana was saying, where the model, when you produce an image, the model will go to this. And these are arrays. So you see this is a 4 polarization by 128 channel array. And each line is one timestamp, one baseline, basically. Okay, so it's important to account for these 3 columns in the data. Data in the measurement set, data, corrected data, and model data. Okay, why first referencing is not enough. So what we have been doing is having a calibrator, an outside calibrator. This is the field of view. And we are nodding between one and the other. So we change between phase calibrator, target, and so on. But there are effects that are not accounting with this. First, atmospheric differences. Even if your calibrator is very near, you usually have different atmosphere response or transfer here. So nodding from one to the other, you are looking through a slightly different ionosphere and troposphere. So this will create a different, you will need a different correction from what you get from your calibrator to what should be applied to the target. The closest the calibrator is to the target, the lower will be these residuals, but they will always be there. And the other thing is that even if you have scans of your phase calibrator, like here, and you can trace the more or less long-term variability of, in this case, the phases, you see that there may be also internal or shorter term variations. And you cannot account for this if you are fitting, just interpolating the solutions of a phase reference calibrator. So because you will have these residuals always within the scan, so in shorter time scales than from scan to scan, you will always have residuals. And all these residuals have a very important effect on the data. It depends a lot on the quality of the data, the quality of the atmosphere, the phases, and so on. But you can have something like this. You have a source, you produce the first image, as Christina did, and then you get something like this, full of stripes. Of course, this is not noise, Gaussian noise, so there is some residuals here that we need to correct. So how do we correct this? Well, you have to think that self-calibration is just calibration. There is no actual difference between one or the other. You are just doing exactly the same that you were doing yesterday. So what you are going to apply is gain cal and apply cal to solve for the gains, the residual gains that will affect the data. But the main difference, one of the main differences, is that you need a model. The model is one of the most important things you need for this. And you need a good model, specifically. So this is an example, again, visibilities. You need to look a lot to visibilities to understand the data. On top is before any correction, and after is after normal calibration. So this is amplitudes for 2 calibrators and a target. And of course, the calibrators, you know, that are point-like sources like this, or slightly resolved. But you should know the structure of this. But you see that the targets can be anything. For example, in this case, you have a lot of emission on the short baselines, which means that you have a lot of extended emission, probably also some compact emission, but it's not clear. But what I mean is that this is much complex than a simple assumption of the calibrator that is just a point-like source, so a flat amplitude with UV distance. And with phases, it happens something similar. For calibrators, you know that the phases should be 0 or very close to 0. But for target, it can be a mess. Phases can be a mess. And this is not random noise. This is not just wrong phases or anything like that. This is the real structure of the source. So you can see here some structure. And this is a mess, but it's a real mess because the source is like that. The phases are like that. So in summary, if you have a point-like source, you will have something flat. Here there are some problems in the data, I think. But this will be flat. And if you have a complex source, this can be very complex. And the problem is that if you do the normal gain cal, as we did before, you are assuming that the source is flat with UV distance. So it's a point-like source. And this is not true in this case, for example. So what happens if you are assuming that your point-like model is, I don't know, 1 Jansky here, you have to decide where to put this, and you will never be right, because when you apply the corrections will try to put all these baselines up or all these baselines down, but you will never have the correct correction for all the antennas. So that's, you cannot do that. What you need to do is to find first the model. And then with the model, here you will have, this is UV distance, amplitude with UV distance for data, well, corrected data in this case, and for the model. So you see that there is complex structure. Here there are some bumps. Maybe it's a bit difficult to see, but there are some bumps, and then all this tail, and then this double blob here. And this is the model. If you have a perfect image, this is not a perfect image, but still it's a good image of the source. You will have a model that tells how all these visibilities should behave in the Fourier plane, so in UV distance. And then what you can do is divide one by the other. You see that it follows almost the same shape. When you divide them, then you have this kind of ratio between both that should be very close to 1. And as you can see, this is now very similar to what we had before with a perfectly point-like phase reference source. We have a source that has amplitude 1 over the whole UV distances. And then here is where we can apply the gain cal and start the calibration, the self-calibration in this case. It's self-calibration because you are using a model of the source that comes from the data itself. Okay, so here you see that this is not perfect. There are still residuals, and this is not close to 1, which means that probably we have not cleaned all the flags here. And this happens because the first image you obtain usually is not perfect, so you may not be able to clean all the structure of the source. So there will be residuals, and that's why this is an iterative process. And well, the self-calibration procedure, there are a few steps to follow. It's very simple. There are 3 steps, but I will explain how to do the whole loop. So you start with creating a source model. As I said, the sources may be complex. Maybe they are not complex, but maybe they are not in the center of the field. So even if they are a point-like source away from the center of the field, you will always have phase slopes with UV distance. So you need a model. You need to know where your source is and what's the shape of the source. So you start by creating the source model with T-clean, and this is what Christiana did before. So we are now at this stage. The second is make sure that the model column in the measurement set is populated with the model image that you have constructed. I will show all these steps now. You can do that with T-clean, and if not, you can also do it at a later stage with FT. Then you run gain cal to find antenna gains, you apply those solutions, and then you have to assess if this correction was right or not, and maybe adjust the parameters. And then you can start again with now, after applying these gains, the image will be better, so you can produce a new image that has a better model and start again, gain cal again, apply cal again, and do this circle several times. This is also a different way of seeing it. You have the observed visibilities are affected by some residual gains, which we assume that are antenna-based, and they are corrupting with respect to the true visibility of each baseline. So what we do is, from the observations, we create a model with T-clean, we gain cal to obtain the gains, we correct the data just by dividing by these gains with apply cal, and then we start the cycle again. Okay, remember that we are always, in this regime, we are always supposing to correct residual errors. We are not correcting large errors because most of that will be corrected by the normal calibration with an external calibrator. Just the CASA pieces. What do we have in CASA to do this? Remember, the measurement set has different columns: data, model, and corrected. The CASA tasks we are going to use is T-clean, gain cal, and apply cal. We are going to produce calibration tables. So this will be files, well, in fact, directories with the corrections, table 1, 2, 3, whatever we do. And then the images. Remember that we have the image is a sequence of several things: the image, the residual, the model, the PSF, and so on. Okay, so now let's go step by step. With the T-clean, what we are actually doing is getting from the data, using T-clean, we get a model image. Okay, so this is what we do. This is another example, the dirty image. This is the dirty beam. We deconvolve and we get this first clean image. And you see that you can see the structure of the source, much better than in the dirty image, of course. But the noise is not Gaussian. There are some artifacts here. There are some stripes and there is, well, it's a mixture, but this is not Gaussian noise. This case is relatively good, but other cases may be very bad, like this one. This is the image and this is the residual, and you see that all these stripes are not noise. These are, as Ivan was mentioning yesterday, it's like a convolution of a residual beam error with the position of the source here. So we need to eliminate this. Okay. The next step is to populate the model column with T-clean. When we run T-clean, remember that we are producing all these images, and this is the image that we want to use. This is the model image. This is Christiana's image from the talk before. This is the image that you get. You see that the noise is not Gaussian. There are some artifacts here that's what needs to be corrected. And then the model image. Also, following the discussion before, in CASA, you don't have clean components as you have in apes, sort of. But what you have is a 2D image. So this is a full image with the same size as the original image, and the model is embedded here with basically the pixels of the image. So if they have flux in some pixels or not. Of course, there can be here, the structure can be much complex than what you can easily do with clean components. You can add here, for example, Gaussian components or elliptical or whatever you want, because it's a 2D deconstruction. In fact, it can, if you produce the image with 2 Taylor terms or more Taylor terms, the model will not be a single image, but you will have an image, a continuum image, plus a spectral index image. So in the end, the model will be a representation of what you think the source looked like at this point. So remember, T-clean, if you apply safe model equal to model column, then when it finishes at the very end, you will see in the log that it says saving model column. And then the model column of the measurement set will be filled with the Fourier transform of this model that just calculated for each visibility in your dataset. If this doesn't happen because you forget this, or because you want, or because you have another image that comes from a previous observation, for example, or anything like that, you can do it manually with FT, which is Fourier transform. You need to select your measurement set, the field you want to correct, and then the model. The model here will be the file that was produced by your imager. If you are using two Taylor terms because you have enough signal to noise that you can trace the spectral shape of the sources or the source, this model will be a list, will be image1.model and image.tt0, which is what CASA produces, and tt1, which is the spectral index representation, more or less, in the model. So this model can have multiple components here, but remember to use two Taylor terms to account for that spectral shape. Okay, so what you need to make sure is that after tclean or FT or whatever you want, the model column is filled with data. So these are the columns in your measurement set. You have the data corrected and the model. So the black one here is the data with a lot of averaging, but it's the data. And this is the model. And you can see that it traces most of the emission very, very well. This is a well-behaved source, so it happens. But at the beginning, especially if your first image is not very good, the model will also not be very good. And so probably you're not tracing everything in such detail, but in this case, we do. Okay, the next step is just to find the antenna gains. For that, we use the data divided by the model. Remember that we need to correct for these strange shapes that we can find. And we apply gain cal to obtain a gain cal table. You can call it the name you want, but basically it's the gain cal table. A few parameters in gain cal, well, you have already seen how to apply gain cal in yesterday's lectures, but basically you need, you're producing a table, so you need to give it a name, you need to specify your measurement set, and then there are a few parameters like SOLIN, solution interval. This is an important one, we will come back to that later. If you want to combine some of the data, for example, spectral windows, well, here you can see spectral windows or field or scans and so on. Reference antenna, this can also be a list, as we saw yesterday. Ref and mode flex means that you allow it to change from one, when, for example, if you have a list of antennas, if the first one is missing, you will use the second one. But be careful if you use this for polarization. I think it can mess things up in some cases. Then the minimum baseline per antenna, the recommended is for phase self-calibration use 3 and for amplitude use 4, because in the end you need 4 values to solve for that. And the minimum signal to noise, I will also talk about that later. But as you see, the parameters are exactly the same as before. There is nothing special. The only difference is that instead of assuming a point-like source, you are assuming, you know that you have a model, your source has a structure, so you need a model and you divide by that. Okay. What you get after gain cal, always check the log. In the log, you will have something like this. For each spectral window, it will tell you the statistics of the solution. So how many were expected, so how many blocks you can divide your data into, how many were attempted, which means these except, but not counting everything that was flagged, and then succeeded is how many good solutions you had. If you don't have enough signal to noise, maybe this number will go down by a lot, and that means that you're not finding all the good solutions and you will flag data. So you have to be careful with that. Okay, this is an example of the gain table for phases, for self-calibration. And what you can see is the phases are always close to 0 because remember that we are solving for residual phases. So most of the huge correction, the huge variation that grabs the phases and so on, it's already been corrected by the first referencing. And here we are correcting for residual phases. But still they can be quite large in some cases. And even in some cases, maybe there was a grab here. I think it happened. Maybe the main calibration introduced a grab in the phases that we can correct now here. And this is an example of amplitude solutions. So they change more slowly, but there is also short-term variability that you can correct and improve your image with. You have to look for large outliers when you plot the solutions for the amplitudes, because with phases we have closure phases, so everything is always restricted. You cannot go crazy, but with amplitude you can go crazy because you are multiplying 2 gains and divided by 2 gains, so using 4 antennas. So you can make one very big by making the others very low, and there could be outliers. So be careful with that. Okay, let's go on. Apply cal is just to apply those solutions. So we have the data column, and we are going to construct or update the corrected column with apply cal using a calibration table. An example of the parameters in CASA is the most important thing is you see that the field can be empty, because now I'm assuming that we are working with a measurement set that only contains your target. You can forget about the rest of the sources because you are now self-calibrating with itself. So you can forget about the rest. So these are the important parameters, which is what you are going to apply. And we are going to apply the calibration table we have found. Gain field can be empty because it's the same field, it's the same source. Interpolation, because you are going to correct from the same data, you don't need to interpolate really, but you can set this in time and frequency if you want. Spectral window map, I will come back to this later. And you can calibrate the weights, of course. And remember that apply cal will flag data. If some solution failed, that will be a flagged solution. So when you plot the solutions in plot MS, for example, you can also plot the flagged solutions, and you will see that some of them are flagged. Okay, so remember that. So you may want to create a flag backup automatically before applying apply cal. And then in the log, you can check things for messages like this. So this is a G Jones, so this correction. The name of the table should be here, but it was too long. And you will have statistics on what amount of data was flagged before this correction and after this correction. In this case, you see that the increase is very small. So that means that you had good solutions for basically all baselines at all times. But sometimes this can increase a lot. If this increases by a lot, I don't know, 10 to 20% or something, that means that you are losing a lot of data because you were not able to self-calibrate. So you may be, you will have to be careful with that. Okay, and then the last step is after you have applied this, you have to assess and adjust what you have done to see if you see an improvement, for example. So one thing you can do is to produce an image and see, measure the noise, measure the dynamic. More than the noise, I think it's important to measure the dynamic range. So the highest pixel with respect to the noise, and even better, you can measure the highest pixel to the most negative pixel, because that will give you a lot of information on the residuals of how non-Gaussian are your residuals. Imagine if you have a huge image, the noise, the global noise will be lower, but maybe you have just right next to the source, maybe you have a huge negative there because it's not correctly corrected. More things that you can do is manual flagging. Maybe you need to flag a few more things because now the data is more clear, is more corrected. You can maybe able to flag a few more things. I recommend, please, always use an external file. Ilse has been saying it several times these days. You can flag interactively with PlotMS, for example. I recommend that you don't do that because it's very, if you are lazy, you shouldn't do that because that's very comfortable. You do it very quickly, but I can assure you that sooner or later, for sure, you will be able to repeat a calibration. In some case, you will need to start from scratch or repeat the flagging. And if you have to do it interactively again, you will say, I should have saved this. So you can use a manual flag file, you can call it any name, and write the commands, exactly what you want to flag, this time range, this antenna, this field, spectral window, channel, and you can describe it in the file, and then in flag data, you just need to load this file, and you will have exactly the same flagging without repeating, without human intervention, and you will make sure that you are doing what you were doing before. You can also use the automatic flaggers like AO flagger, but in CASA in particular, you can use flag data, the standard one, but with mode TF crop. And this will find outliers in the frequency and time space, and then amplitudes that are, in this case, away from 4.5 sigma. And in general, it's very useful. So, and the flag dimension is frec time by default. So I recommend you're doing this specifically with the data column selected residual. Residual means corrected minus model. So even if you have a very complex source, let me show you this plot, a very complex source, because you are now dividing by this, you can flag on the residuals and it's much more efficient. Also, being here, always inspect your data after self-calibration. Let me show you two images that are very similar before and after correction. So for example, this is the model and you see that the visibilities here are away from the model, but the rest is more or less okay. After self-calibration, what will happen is, if you look here, the data will go to follow the model. So that's why it's important, and this is very important for arrays with low number of antennas, because you don't have so many restrictions, you are forcing the data to look like your model. It can happen that if your model is not good or your signal to noise is not good, you will mess the data. So the data may be corrected. So you have seen, if this is correct model, then it's perfect because the data is going right there. But imagine that your model is not right and it goes up like this, for example, I don't know. Then your data will follow exactly that curve. And that's dangerous because you have to make sure that the model is correct. Otherwise, you will be creating fake sources in your image. Okay, we have a lot of things to do. Okay, what we need to do is iterate because this is several loops. Usually with only one self-calibration, you don't have enough. So I will show you more or less what you can do. So you start with a measurement set. I recommend that you start with a measurement set. So you split the data. In CASA is MS transform. So you split the data after the normal calibration and you work with an independent measurement set with all the corrections applied before. You don't need, but I recommend doing that. Then you run tclean, produce a new image, including the model. Then you run gaincal to produce a table. You use this table in applycal to correct the measurement set. And then with the corrected data, you can split again. So this is MS transform again and produce a new data set, or you are ready to, let me show you this. You are ready to image again. So this is important to follow the logic. So this step populates the model column. This one uses the model to produce a calibration table. This one applies the data, applies the table to the data column to produce the corrected column. And then the corrected column can be used to image or to split and so on. Usually we will follow this loop here, produce a new image and then start again. So cycles. The important thing is that the model, your initial model may not be very good, very accurate because you have a lot of residuals. So the important thing is that you never overdo the model. If you're not sure, as Christina was saying, if you're not sure if one feature is true or not, don't clean it to avoid including noise in the model. So you start first with a more smooth or more mild self-calibration, for example, with solution intervals of the full scan if you need, or 64 seconds or something like that. You do the whole process and then you go to the second iteration. And then in the second iteration, because your model is better and you are more confident with your data, you can use a shorter solution interval and see what happens and see if the noise goes down. You always have to check that the dynamic range goes up and the noise goes down. Then when the phases, you may do several of these loops, and when the phases are right and are correct, you can start with amplitude. Amplitude is more restrictive, you have more degree of freedom, and also it's not so well constrained. So usually you should start with very long solving. The solution interval could be even the full observation, just to align the antennas a little bit more. For that, you need to combine scans to combine different scans during the observations. And then you can continue, you can repeat this several times. For example, now we go to shorter solution intervals, but combining the spectral windows, or even shorter solution interval. This is the shortest one in integration time. So this is not just how many integrations you have. And here we are combining spectral windows and also polarizations, because you can only do this when you have aligned the phases before. And then maybe with that, you can do an amplitude and phase with solution interval of infinite without combining scans, which means one solution per scan. Okay, how to implement this? I think I will be very quick. There are different ways to implement these loops. One is fixing the corrections with a split or MS transform in CASA at each iteration, but this produces a lot of data and I think it's not worth it because you don't gain anything from this. Another is to work always with the original data and only update the model. So finding the corrections from scratch in every cycle. And then the option I recommend is the incrementally adding more tables. It's easier. just to have a feeling of option 1 means when you end the cycle, you produce a new measurement set, and then with the new measurement set, you do another cycle and produce another one, and so on. So here you are multiplying the data very quickly, so I don't recommend it. The second option means that when you do a cycle, you produce one table, but in the next cycle, you produce a new table from scratch. And this is not recommended because usually amplitude self-calibration needs longer solution intervals. So that means that if you are producing this table from scratch at some point for amplitudes, the phases will not be corrected properly, and then you will have that the amplitude correction will compensate for this, the coherence, for not having the correct phases. So my recommendation is use this cycle. The first iteration, you produce one table. In the second one, when you are computing the new table, you add the previous tables. You will see this very easily with an example. This is gain cal, this is producing tables, and this is applying tables, okay? So cal table, the one that will be produced is called 01. And in apply cal, we are going to fill the gain table value. So this is the one that is going to be applied. In the second run, you are producing version number 2, or calibration table number 2, but based on the corrections that were produced in the previous step. So when you apply both of them. And then in the third, you use the previous calibration to create the new one. And when you apply everything. So it's iteratively. The good thing about this is that the first one will have the largest corrections, and then the second one will have second order corrections, and then the third one even minor. So you can see at some point you will see noise, so not really correcting anything else at some point because everything is correct. So I want to show you why we are doing this, the self-calibration improvement, so how data is improving thanks to all these loops. So this is a first example. This is just by using the phase reference calibration. After one phase iteration, you have a better image. You can see the structure much better than here. And then after the second phase self-cal, you can see the structure even better. And then with amplitude, you can see the source as it is. But you see that this is still not perfect. There are residuals here, so you may want to do a few more cycles of this. With VLBI arrays, it's typical that because you don't have many antennas and because the models can be complex in some cases, you need to do this slowly and do several cycles. But the improvement is clear. This is the image I showed you before. After self-calibration, you have this beautiful noise. Maybe it's not perfect because there is some maybe diffuse emission here, but it's much better than this one, of course. This is another example, gravitational lens source. The noise before and after, you see it's improved by a factor of 3. And the noise, the important thing is that the noise that you find in the end should be as much Gaussian-like as possible. There should be no artifacts, no things like that. This is an example, I think, from the VLA, but you can see that all these stripes can disappear and then you have a good noise. Okay, talk about choices. How to, you have to make a lot of decisions when doing self-calibration. And the problem is that there are some rules, but each source and each array will be different. So you have to understand the process. That's why I wanted to show you the whole process in detail, because you need to understand it to make these choices. The first one is the solution interval. This is easy, is as shortest as possible, as long as you have enough signal to noise. So if you can find solutions every 3 seconds and you can follow the shape perfectly, use 3 seconds. If not, you may need to use longer solution intervals or longer ones. It's better to use you could reduce the signal to noise. You will see it now. If you're including solutions with very low signal to noise, your data will not be corrected properly. So you can go to 3 seconds, but what will happen is that you will end up flagging data if you don't have enough signal to noise. This is an interesting plot in which this is the distribution of signal to noise of the solutions from one calibration table for different solution intervals. So of course, if you are using all the data in 48 seconds, you will have a lot of signal to noise. So all the solutions are up here, so everything is good. But as you go down, the signal to noise of your solution, the average one, is going down. There is this mean signal to noise ratio parameter in gain cal that cuts the solution with lower signal to noise than that. So you can do the trick. Maybe you're not getting enough solutions and you say, okay, instead of using a mean signal to noise of 3, I will use 1. You will have more solutions, but those solutions are not going to be significant enough. So I don't recommend doing that unless it's necessary for some reason. But
sorry, Javi, 5 minutes.
Okay, so this is a way to find out how to reduce it. In the end, what you have to do is to plot the table. You can in plot MS you can plot the solutions, but also the signal to noise, and then you can see the signal to noise of your solutions per baseline, and decide what is the signal to noise ratio you want to do. How to decide the loops, which loops to do? Well, the important thing is always start with phase only self-calibration. Because you need good phases before you start calibrating amplitudes. Because the reason is that, well, I already said that the amplitude corrections will compensate for the correlation. If your phases are not right, you will have the correlation, and then the solutions, the amplitude corrections will try to push that up, and that's not real. So don't run amplitude self-cal until your phases are good and your model is as good as possible. And even in that case, the first run, don't try to overclean the image, because you have to make sure that the model only contains real data. I have said that several times, but it's very important. And then progressively decrease the solution intervals and check. You have to check the image, the noise, the dynamic range, the solution, how many solutions failed, and so on, to try to compensate by that. Sorry, not use too short solution intervals, for example. Okay. And when to stop? When do you end? Okay. Remember that complex sources may require several cycles. You will need to iterate through this several times. You have to stop basically when no further dynamic range improvement is achieved. So at some point you will not be able to go shorter in solution interval, and that's when you need to stop and try to reach the image quality that you need for your science. Other practical considerations, you may use this parameter combine in gain-cal to boost your signal to noise. So you combine scan, for example, when you have amplitude self-calibrations that are longer than the scan, you can combine several scans and have more signal to noise. You can also combine spectral windows. This is common to do in phase self-calibration only when the phase offsets have been removed, because each spectral window may have some residual offset, but if that's corrected, which usually is, even with normal calibration, you can do it. But if you do this, if you combine spectral windows, you need to use the spectral window map parameter in apply-cal. I don't have much time to talk about this, but basically what you are seeing is, because I'm combining all the spectral windows, I will only have solutions for the first spectral window, which is number 0. And a spectral window map is saying, when you correct the rest of the spectral windows, use solutions from spectral window 0. So this is saying, to correct the spectral window 0, use solutions from 0. To correct number 1, solutions from 0. From number 2, solutions from 0. So if you're doing from amplitudes, combining spectral windows for amplitudes, make sure that you have a very good model with a spectral index included. So you need to use MTMFS, multi-frequency synthesis. So your model has all the correction. So this is basically using 2 Taylor terms. And now there is a mode that was recently, a couple of years ago, was included in CASA, which is T, that allows you to also combine parallel hand correlations. So, for example, RR and LL are combined, and you gain a factor of square root of 2. Okay, this is another practicality, that when you are doing the apply-cal step, I've said that you have to include all the previous calibrations. So if you are in the 5th loop, you will include the loop calibration table number 1, 2, 3, 4. Then maybe you need to fill the linear, so the interpolation method on the spectral window map. And this can be a bit messy, and this can mess a little bit your script if you are working with a script, for example. So there is an alternative, which is using do calib true. Instead of false, which is the default, you use true, and then all this is written in an external file. You can call it whatever you want, and it looks like this. So you say the name of the cal table, if you want to calibrate weights, interpolations, spectral window map, and other parameters. You can add more parameters. And the good thing is that this is stored in an external file, so your script will be much simpler. You just call this, and that's it. And also when you are writing scripts, it's very easy to fill this calib file. So every time you run a gain cal and produce a table, you write a line here, and then when you apply, you will apply everything. And this is also useful because it's a very easy way. If you have imagine that Jack will talk about this later, but if you have in the field of view, you have other sources that may be used to self-calibrate other sources in the field because it's bright enough. You can create all these tables and then just apply all those to your targets immediately with a file like this. But this is just an option. You can do it or you can do it in this mode. As I said before, never include noise into your model. This is very important. This is an example, I think, from the VLA. But if you have an image, you will always, if you have a big image, you will always have bright pixels. Just by statistics, you will always have some bright pixel at some point. If you think this is a source and you clean it and it's included in your model, when you self-calibrate, especially if you self-calibrate with not cutting low signal to noise solutions, all the flags that gain cal can find will go to that point. So even if this is not a real source, the gain cal self-calibration will try to put as much flags as possible here. And to avoid that, you have to be careful, either not clean noise or use high signal to noise ratio. So you have to make a compromise here, but never includes noise in the model. Another thing is amplitude normalization. When you are, this is important, the amplitude self-cal, what you are solving is for the time-dependent gain residuals, but not for the flux scale. The flux scale should be fixed by the main calibration, and you should not alter it in principle. So it can happen that models, because the first iterations are not very, the model is not very nice, you may not clean everything. Remember, Christiana couldn't clean at the first iteration. There was some part of the mission that was not sure if it was real or not, and it's better not to clean it. And then the model will underestimate the total flux of the field. And then what will happen is that your flux will be lower, and if you calibrate the amplitudes, you may be altering the flux scale. So by normalizing the solutions, you avoid that the flux should change in principle. And then I think this is almost my last slide. There may be other sources in the field of view. So for example, this is a 30 arc minutes, the primary beam of an L-band 25-meter antennas, more or less. And maybe you are interested in a source here, but it's very faint and you cannot self-calibrate. But maybe there are other sources in the field. Here you can see some of them bright sources. So if you are able to find out this beforehand, or you know this beforehand, or well, basically you can use this source to self-calibrate the field. Again, because it's the same field, the same observation, you are going to self-calibrate on the same data. So not interpolating anything, just write on the data. And then the solutions, you can transfer the solutions to your target and it will be much more accurate. For VLBI or the EVM, for example, you will not be able to do a full image of the whole field of view, but you may request multiple phase centers. So if you know that there is a bright source nearby, which is very strange, but may happen, you can use that. You will see it can happen in the next talk, of course. And just to conclude, self-calibration is a very powerful tool, but it's also dangerous. So be very careful. But you have to think that this is based on very in the interferometric principles. So this, as I said, self-calibration is not different from calibration. So all this is safe as long as you know the assumptions and as long as you are including only real data, a good model, and you are being careful with that. But you have to be a bit, take care of that. You will need this to extract all the science from your data. It's very difficult to extract all the information that you have in a data set if you don't correct to the maximum level of self-calibration that you can. So phase referencing is usually not enough for some cases. I haven't mentioned it, but be careful because self-calibration is especially tricky for astrometry because you are making your data look like your model. If your model is not good, the source will move to the position of the model. So if the model is not at the right position, then your source will also move. So be careful with astrometry also. And the quality and reliability of your science output depends on on understanding all this process. So I think it's important to know that. And that's all I wanted to say.
Okay, thank you very much. It was an instructive lecture on self-calibration, and we had a few questions. We still have 10 minutes to answer them. I think you just actually half answered one of them, so
That's
we may
right.
start with Adil's.
Yeah, that was indeed a question about the positional accuracy. So you lose your position information, and the question is there a way to recover this?
The thing is that you will not get a better position than the one you get from phase referencing. So phase referencing will give you an initial model, and that position is what you can get is more signal to noise. So in the end, the astrometry accuracy will depend on the signal to noise of the source. So what you can gain is that, but everything will rely on the phase referenced position. So the phases that are transferred from a calibrator that you know exactly what it is. Everything that is done after that depends on the quality of your first iteration, basically. But still, you can gain some signal to noise in there.
Okay. Then let's go. There were a few questions in the Q&A which have in the meantime also been answered by Ivan, but I think it's worth going over them in a plenary way because they're good questions. The first one is Carlos Stangalini asking if he understands correctly that the self-cal in CASA can take into account the spectral index of the source model.
Yes, in the end, self-calibration, what it's doing is just dividing your data by the model. So the more information is in your model, the better will be that division. So yes, because the model, that's the important thing about CASA. The model is, the measurement set has a model column. That means that it's not clean components. It's not a point with a spectral index, another point with a spectral index. What it is actually the convolution of the model. So each visibility will have a model visibility, and that model visibility can have as much information as you want. Work produced with as much information as you want. So if you have a spectral index, that will be incorporated directly in the model column. That information will be there.
Does the model column include convolution with the primary beam, or is it just the Fourier components of the model, the clean component model?
No, it doesn't. It doesn't include. The primary beam correction is done after the model is constructed, so it doesn't include it. It's just the Fourier transform of that.
Yeah. Okay. Good. Another question that was asked is which parameter in GainCal tells CASA to use the model stored in the model column?
It's always done. It's done by default. What happens is,
that's what Ivan says as well.
Yeah, the measurement set will, well, at the beginning it doesn't have a model column, but as long as you start using calibrators, you will have a model column. And what will happen is for calibrators, it will be all amplitudes 1, all phases 0, until you put the flux scale, of course. Yeah, that's it.
Yeah. One of the earlier questions that we have skipped over.
Can I add a comment to that?
Oh, sure. Yes.
So that is a bit tricky because all calibration tasks in principle use the model column. So if you have a model and did self-calibration, created a model, and then say go back and to fringe fitting, the fringe fit task will actually use that model, which may or may not be what you want. So it's important to then delete the model column if you don't want it. When you go back, want to repeat a step and or back up and repeat the step and go from there.
That's a good point.
You can always clear the model column with the task clear cal.
Yeah.
Yeah.
And you can also clean the corrected column if you want.
The question that I was about to ask is how much amplitude variation of the gain solutions is allowed?
Well, there is no restriction to that. If you think, you have to look at the solutions, and if you think that the correction you are seeing is real, then in principle there is no limitation. But usually from a standard calibration, all the gains should be good enough so that the amplitudes are not too bad. Let me show you. Sorry, I lost my amplitudes. Well, what I wanted to say is that residual amplitudes should be always close to 1. Sorry, I don't find the plot now, but everything should be close to 1. There should be a deviation of 10%, 20% maybe, but not much more than that, especially if there is an outlier. So amplitude variations will be more or less smooth. So there shouldn't be outliers. If there is an outlier, you should flag it. In CASA, there are tasks to smooth solutions, but in general, if there are outliers going outside, I don't know, 30%, something like that, just flag them because they are probably not real. But that depends on how was the original calibration. If there are huge residuals, which is not normal, then this can go to 10, 20% easily, even more. Yeah.
Okay, so there.
May I add maybe a comment about this? So one of the reasons that could make amplitude corrections or self-cal amplitude corrections high would be, for instance, problems with the pointing of the telescope. And this may be especially important at high frequencies because the beam is narrower and it's harder to keep the pointing of the antenna. So we could have the case where we can have, for instance, we have seen that in the 1 millimeter global VLBI with the EHT observations. There was one antenna that had problems with the pointing, and we could have corrections or of maybe 30, 40%. Okay, but this is pathological. Okay, and this doesn't happen. Doesn't happen often. Okay, so you often only have correction about, let's say, 10, 20%. Okay, but you could have actually real solutions that go beyond that because of, for instance, pointing problems.
Yeah, really good point. Yeah, thank you.
And if I can add also, for the ABN, at least regular observation, we typically try to verify all the gain calibrations for the telescopes, and we try to restrict them to, the same 10, 20%. And typically, if one station, we may expect that one station exhibits a much larger offset, like 30, 40%, you typically have a comment in all the metadata that you have from the experiments. So you should already warn that, okay, you may expect a much larger offset in gains, and then you can still keep it because probably it's valuable data, but just requires a larger one. But in the typical case, if you don't have any warning like that kind, everything should be within 10, 20%.
Here you can see an example of the solutions. I hope you can see the number 1, value 1 is here or here. And everything is around 1, but there can be, this is a 5% offset, 10%, even up to 15%, but this starts to be more like outliers. So yeah, around
that. Sorry. So on the Mattermost, there's a question about combination of EVN and eMerlin data. Are there any general tips on how to handle this in self-calibration and what to do with if there's lacking system temperature information, so the scaling is off?
Yes. So, well, the basics are the same. You need a good model. And the problem is that usually because you are tracing so very different angular scales and resolutions, the model may be quite different from the highest resolution part to the lowest resolution part. So I think what is more important is that if you are combining the two data sets, because they come usually from different calibration, unless you are observing all at the same time, you need to be very sure that the weights of the data are properly aligned. Because if not, when you produce the first image, it will be dominated either by the very high resolution or by the very low resolution. And you need to take that into account. So just by playing with the weights or recomputing them will allow you to have a better initial image. And then with that initial image, you will find the phases. And then the first amplitude self-calibration will be critical precisely for that, for aligning if there are some mismatches in the flux scale of both. Apart from that, probably you have to be very careful with the model and probably using multi-scale cleaning will help produce, depends on your source, but multi-scale cleaning will help you recover all the flags. So what you have to do is to plot the visibilities, for example, amplitude against UV distance and the model, the data and the model, and see if there is some mismatch or if the model is really missing some part of the data. But apart from that, the process is the same. Just be a bit more careful because there may be some offsets in the flux scale.
Okay, I hope that answers the question. Do we have time for a few more, Benito?
We can leave it here maybe and have a 30-minute pause because there are a few more questions, so maybe we can just answer them directly, Mattermost.
That's also, there's 2 more on the Q&A. I will move them into the Mattermost channel and we'll handle them there. Before we go into the break, I've got a few logistical announcements for today. So today, after the lecture by Jack this afternoon, we'll have our social event. So we're jointly walking across our local area. And the infrastructure for this has all been posted on the wiki page. So check out how to handle your step counts and how to forward us the information. And it's really nice that this framework also allows you to upload pictures. And since we're all working in CASA this week, my suggestion would be that everybody who has the opportunity uploads a picture of their house, the outside or the inside, to the walk. And we will also use these for the final conference mosaic picture. In the Mattermost general channel, Olga has posted a link for you on how to upload any other images that you can use for this mosaic. So feel free to start sending us pictures. The more we get, the better the mosaic will look in the end. And that's it for me.
Okay, then we will have a break of 30 minutes and then we will see that 12 local, 11 UT for the data processing. See you. Okay, see you later.
See you.